and I will share my screen. Okay, I will share my screen. Okay, can you see my screen? Can you hear my voice?
Yes, I can.
Okay, thank you for the response. Okay, so last week we have stopped here. Okay, last week we have stopped until this slide. So actually we stopped until this slide. So now we're gonna proceed with example 3.2. So now we are still in the topic of AM power calculation. Okay. So maybe before we proceed about this topic, maybe we need to refresh again what we have learned in the previous weeks. Okay, what we have learned in the previous weeks. So power calculation, this one. Okay. Wait. Okay, power calculation, as I explained in the previous week, in order to calculate the total power, you need to know the complete equation of AM. Okay, so for example, we have learned okay, wait, maybe sorry. So if you remember that wait. So VAMT, remember that for double sideband full carrier we have VC sine 2 pi FCT. So this is VC plus VM over 2 cos cos 2 pi FC. Wait. FC minus FM. This is for the lower sideband, and then minus VM over 2 cos 2 pi FC minus FC plus FM. Okay, so from here, once you have defined the complete equation of AM, then you can calculate the total power. Okay, so VM over 2, remember VM over 2, VM over 2 is equal to MVC over 2. Okay, MVC over 2. So you see that in order to calculate the total power, we can take the peak amplitude of each component. So if you see from here, I have VC, I have VM over 2, I have VM over 2. Okay, so I have 3 components. And if I draw the frequency spectrum, okay, if I draw the frequency spectrum, so the spectrum consists of 3 components. Okay, VC, VM over 2, and also VM over 2. Okay, so from here I know that the total power might consist of 3 components. Okay, the carrier, the lower sideband, and also the upper sideband. So the total power P total is equal to P of carrier plus P LSB plus P USB. Okay, so from here again the equation for power is V square over 2R if we use the peak amplitude. Okay, in the equation we use the peak amplitude, or if you use the RMS, it's gonna be V RMS square over R. Okay, so the equation use, okay, the equation uses this peak amplitude of voltage, so we're gonna use V square over 2R. Okay, So this one PC is Vc square over 2R, like this one. Okay, so Vc square over 2R, and here is MVC square over 2R, okay, which is this one. Okay, so wait. VC square over 2R. Okay, VC over 2 to R. VC. Okay, sorry. So we have this is you can see that this is LSB, this is PUSB. Okay, so why it is MVC? Okay, MVC is from here, from this MVC over 2, so it is actually so VM over 2 divide over 2R, so this is equivalent to MVC over 2 square divide with 2R. Okay, so that's why MVC square over MVC over 2 divide with 2R. So that's why we get this one. Okay, so from here we can see that we can rearrange the equation to become in term of carrier power. Okay, kalau kita susun, kita boleh dapat dalam sebutan carrier power. Okay, because if you see from here, we can see that here this one is carrier power, equivalent to carrier power. Okay, so that's why we can rearrange the equation to become PC plus M square over 4 PC plus M square over 4 PC. And finally we get P total equal to PC multiplied with 1 plus M square over 2. Okay, so this is only true for double sideband full carrier. Okay, double sideband full carrier. And we have learned that for the double sideband full carrier, even during the ideal case where M equal to 1, okay, the modulation index equal to 1, the carrier power consists of 2 over 3 of the total power, which is very big. Okay, 2/3 daripada total power itu adalah milik carrier power. Okay, so the sideband power, both lower and upper sideband, carries 1 over 3 of the total power, which is very small. Okay, 1 over 3 of the total power. So this is for both lower and upper sideband. And if you want to find each of lower sideband and upper sideband power, it is equivalent to 1 over 3 divided with 2. So we get 1 over 6 of the total power for each of the sideband. So this is even less. Okay, this is less. And during the non-ideal case, the value would be even lower than this, which is not good. Why? Because the information contains in the sideband. Carrier does not carries any information, as I explained in the previous week. So carrier component is like you can assume like empty boxes. So it is empty inside without the information. Okay, the thing that carry the information are both sidebands, lower and upper sideband, and the information is duplicated, lower and upper, similar information. So in double sideband full carrier, it is something like we send the signal twice, as if we send the signal twice. Seolah-olah macam kita hantar signal 2 kali, because the information in the lower sideband is duplicated. The information in the lower sideband is the same as the information in the upper sideband, so it is duplicated, as if we send twice the signal. Okay, as if. So that's why here it is said that this double sideband full carrier is wasted a lot of power, because the carrier where it does not contain any information has consumed the most power compared to the sideband. Okay, ideally the best case scenario is we want the sideband power to be higher. Okay, that's the best case. Okay, we want the sideband power to be higher. That's what we want. Okay, so that's why in this case the double sideband full carrier is considered as less power efficient compared to the other types of AM, because later you're going to see other types of AM where it can improve the power efficiency, okay, where we can reduce the total amount of power, and we can increase the amount of power for the sideband, okay, which is more efficient than double sideband full carrier. Okay, so let's do example 3.2. 400 carrier is modulated to a depth of 75%. Calculate the total power in the modulated wave. Okay, so you are given a carrier power which is PC 400 watt. Okay, PC is 400 watt, and you are given the modulation index. Okay, a depth of 75%, so this is actually referring to the modulation index. Calculate the total power in the modulated wave. So this is actually related to double sideband full carrier, AM double sideband full carrier. So you can use this equation, simplified equation, P total, so this is double sideband full carrier, P total equal to PC in bracket 1 plus m square over 2. So you can put the carrier power 400 watt and then bracket 1 plus 0.75 square. So remember, you should put the absolute value, which is 0.75, not 75. So don't put 75 over here, which is wrong. Okay, students sometimes do careless mistake, they put 75, so be careful about that. Okay, so the total power here is 512.5 watt. Okay, so if you have question to ask, you can ask question. Otherwise, I move to the next example. Okay, example 3.3. okay, so example 3.3, an AM broadcast station's peak carrier voltage of 2 kilovolt has been amplitude modulated to an index of 75% with a 2 kilohertz of test tone. So it is a AM. So remember, if in your notes, if it is mentioned about AM, it is referring to the double sideband full carrier. Okay, so this radio station has a peak carrier voltage, which is Vc is equal to 2 kilovolt, has been amplitude modulated to an index of 75%. So this is modulation index M. So this carrier signal has been amplitude modulated with another signal, okay, which has the frequency of 2 kilohertz, and this other signal is a test tone. Okay, so imagine that carrier modulate with another signal, a test tone, which has the frequency of 2 kilohertz. So that means this is referring to the message frequency or modulating signal frequency, FM. Okay, so the station broadcast frequency is 810 kilohertz. So what is broadcast frequency? So broadcast frequency is referring to the carrier frequency. Okay, broadcast frequency is the carrier frequency, the frequency that you used for transmission. Okay, the frequency that you use for transmission is the carrier frequency. Okay, frekuensi yang digunakan untuk penghantaran adalah merujuk kepada carrier frequency. This carrier frequency is located within the AM, within the range of AM frequency band. If you remember, I told you before that AM frequency band, the range is around 5xx kilohertz until 17xx kilohertz. Okay, so this is the range of AM frequency band. Okay, dalam julat frekuensi ini. So this is AM. AM has a few frequency band. Okay, so one of it is around 500 something until 17 something kilohertz. Okay, so this is the broadcast, the frequency that we use for transmission. Okay, so compute the following. Find the lower and upper sideband FLSB and FUSB. So how to find this? Okay, so how to find this frequency? Okay, so now you know how much is you know FC and you already know FM. Okay, so FLSB is located at FC minus FM. FUSB is located at FC plus FM. Okay, so the frequency is 808 and also 810, which is stated here. Okay, so 810 minus 2 and also 810 plus 2, so we get 808 and also 812 kilohertz. Okay, and then what? Find the peak modulation voltage, Vm. Find the Vm. So we can get Vm based on the value of modulation index and also the Vc. Okay, remember M is equal to Vm over Vc. So Vm is equal to MVc. Okay, which is 0.75 multiplied with 2 kilovolt. Okay, so we get 1.5 kilovolt. Okay, so modulation index multiplied with Vc 2 kilovolt, so we get 1.5 kilovolt. Okay, so this is Vm. And then what? The peak lower and upper sideband VLSB and VUSB. Okay, so VLSB is equal to Vm over 2, Vm over 2, or it is equal to MVc over 2. Okay, so we already calculate Vm from the previous question, so we can use that Vm for this calculation. So that means we already get Vm 1500 volt. So VLSB and VUSB is equal to 1500 divided with 2. So we get 750 volt. Okay, as stated here, 750 volt or 0.75 kilovolt. Okay, so this is 1500 divided with 2. Okay, so we get 0.75 or 750 volt. Okay, this one. And then what? The maximum signal amplitude Vmax. So Vmax is equal to Vc plus Vm. So it is equal to 2000 plus 1500. So this is 3500 volt or 3.5 kilovolt. Okay, 3.5 kilovolt. Okay, so this is the answer. So if you have question about this question, if you want to ask about this question, please ask now. Otherwise, I will move to the next example. Okay, the next example. Kalau ada soalan boleh tanya. Okay. So if you don't have question about this, I will move to the next example, which is example 3.4. Okay. Boleh kalau ada soalan boleh tanya So I move to the example 3.4. A spectrum analyzer with an input impedance of 50 ohm is used to measure the power spectrum of an AM signal at the output of the preamplifier circuit. So you are given the resistance. Okay. The AM signal has been modulated with a sine wave. Okay. So the effective. So this is AM signal. So the keyword here is AM signal. This is using double sideband full carrier. Okay. So the word AM referring to the double sideband full carrier. Okay. So the AM signal has been modulated with a sine wave. The effective power is 750 milliwatt, and each sideband PUSB and PLSB is 125 milliwatt. Compute the following. Ini ada jawapan juga. Okay. So compute the following: the total power. How much is the total power? Okay. So total power, since this is double sideband full carrier, so this is equal to PC plus PLSB plus PUSB. Okay. So we just add up all three components. Okay, so we just add up all three components. So as in the answer here, so that means PC plus PUSB plus PLSB, this one. Okay, so given PC is 745 milliwatt plus PUSB 125 milliwatt plus PLSB 125 milliwatt. So when you add up together, you will get this one equal to 995 milliwatt. Okay. And then what? The peak carrier voltage. Okay. So the peak carrier voltage is equal to how much? So you are given power. Okay, you are given power. So you can find the carrier. You can find the carrier. Peak carrier, which is equal to how much is this? So here it is say that effective power, so it is actually equal to VC RMS square over R. Okay, because the keyword here is effective. Okay, effective power. So it is actually calculated using the equation of VC RMS square over 2R, because this is a effective power. So therefore from here you can see that VC square of RMS over R, this is equal to VC peak over square, so square root of 2 square. So you get this is 2R actually. So VC peak square over 2R times PC. Ini sama lah sebenarnya. So this is actually PC is equal to VC peak over 2R. Okay. So when you want to find the VC peak, okay, so that means VC peak is equal to PC times 2R. Okay, PC times 2R. And then you need to do square root. Okay, square root. Okay. So you can put inside the values. Okay. So PC is equal to 745 milli multiplied with 2 multiplied with resistance, and then you do the square root. So you will get 8.6313 volt. Okay. Please try using your calculator. Okay, try using your calculator. 745 milli multiplied with 2 multiplied with 50, and then square root of answer. So you get 8.6313. Okay. So this is peak carrier voltage. So this is a peak carrier voltage, which is 8.6313 volt. Okay. And then the question asks modulation index M and the percentage of modulation index. So we need to calculate modulation index and then the percentage as well. So until the second question, we already calculate, or we already known Vm and also Vc. Okay, so Vc has been calculated. Do we know about Vm? Okay, we don't know about Vm. We know about Pc. Okay, we know Pc, we know modulation index, so we can use the simplified equation. Okay, we can use the simplified equation, which is this one. Okay, so P total. So we already calculate P total. We know Pc. We know we don't know how much is M. Okay, so since this is a double sideband full carrier, so we can use this equation. For other AM signal, okay, for other than double sideband full carrier, we cannot use this equation. Okay, untuk jenis AM yang lain, we cannot use this equation. Okay, if this is not double sideband full carrier, therefore we cannot use this equation. We need to use P total equal to Pc plus another P plus other types of P, depending on the equations. Okay, so for this method, the other way is to use the to find the Vm first based on the PLSB and PUSB. Okay, there is other way, okay, to calculate the modulation index. First, you need to find Vm based on the sideband power. Okay, from here you can find how much Vm. Okay, from here you can find how much Vm, because sideband voltage is Vm over 2. So from there you can calculate Vm, and then you can calculate the modulation index. The other way is to use this simplified equation for double sideband full carrier. Okay, so if you use this equation, that means the modulation index is equal to square root of 2 times total power over Pc minus 1. Okay, we rearrange the equation, it becomes like this. Okay, so put inside the total power, we have calculated from the previous equation 995 milliwatt, divide with carrier power 745 milliwatt. Okay, minus 1, and then multiplied with 2 square root, so we get 0.8192. And modulation index in percentage, we multiplied with 100%, so therefore we get M equal to M multiplied with 100%, so we get 0.8192 multiplied with 100%, so we get 81.92%. Okay, and then what? Okay, so the next question asks the modulation voltage Vm. So we can find the Vm based on the value of Vc and also the value of Vm. Okay, so we already know Vm, which is how much is Vm? Sorry, we already know Vc. Okay, we already know Vc is equal to 8.6313. Okay, we already know the value of M, which is equal to 0.8192. So therefore we can calculate Vm. Vm is equal to M Vc. Okay, So if you calculate MVC, so this is equal to 0.8192 multiplied with 8.6313. So try to calculate how much you get for this. So 0.8192 multiplied with 8.6316, so 7.07, okay, 7.071 volt. So this is the peak value, okay. So the question does not specifically mention whether this is peak value or RMS value, okay. So in this case, it is enough if you just provide the peak value, which is 7.07 volt, okay. But if the question asks to find the RMS, then you need to find Vm RMS by dividing the peak value with the square root of 2, okay. So you get 5 volt, okay, if the question asks for RMS. For this example, the question does not specifically mention about to find the RMS. So in this case, actually you can give the answer for this one, peak value is enough, okay. So I don't know why the question proceed until RMS, but if the question specifically asks for RMS, you need to divide the peak value with the square root of 2, okay. And then what? Find the lower and upper sideband voltage VLSB and VUSB. So this is actually Vm over 2, okay, Vm over 2. Or you can use MVC over 2, either one, okay. So MVC over 2, so this is actually equal to, we can use Vm, this one, peak value, so 7.0708 divide with 2, so you get 3.5354, okay, 3.5354, which is this one, okay. So you don't need to go up to this one, so this one you need to convert from the VC peak, so it use the VC peak. So if you use a VC peak, that means you need to divide with square root of 2, okay. So no need to use a VC peak, you can use the no need to use a, previously it used the RMS, so based on the RMS value they found the value 2.5, but you don't need to calculate based on the RMS value. You can straight away use the VC peak, Vm peak, okay. So Vm peak, okay, Vm peak value, okay, divide with 2, so you get the value of V lower sideband and also V upper sideband, okay. So this is equal to 7.0708 divide with 2, so you get 3.5354, okay, which is this one, okay. Because VLSB and VUSB is referring to the peak amplitude, not the RMS, okay. In your notes, in your syllabus, the VLSB and VUSB is based on the peak amplitude of the message signal Vm, okay. It is not based on RMS, so therefore better for you to directly use the peak value of Vm, okay. So I got this one, okay. And then what? So if you don't understand, you can ask question, otherwise I move to the next sub question, okay. So the next sub question asks, sketch the waveform that you would see with an oscilloscope if it were replaced in parallel with the spectrum analyzer. Okay, again draw the waveform. Remember, waveform is voltage versus time figures. Waveform is a figure of voltage versus time. Okay, in time domain. Okay, waveform is in time domain. So you need to draw like this. Okay, so as I already explained to you previously, when you want to draw, as I mentioned previously, okay, remember what I do is, maybe I put it somewhere. So I draw the imaginary line for VC. Okay, this is the line for VC actually. Okay, sorry, and then I draw the sine wave from here, imaginary sine wave, imaginary sine wave. I don't know, sorry about that. And then here, so when I draw the wave, so I draw the wave. Okay, so after I draw the imaginary line, then I can begin drawing the waves like this. Sorry. So you need to practice to draw this one. So you need to practice. So starting from here, below. Okay. So when you draw, first of all, I will see whether the drawing is correct. So the drawing is correct based on the height of the wave. Okay, the upper and lower. Okay, so this is correct. That means so I draw correctly, and then I need to label. Okay, label the axis V versus time. Okay, V versus time, and then what? I can find the maximum and minimum. Okay, find the maximum and also the minimum voltage. Sorry, something wrong here. So this is Vmax and Vmin, and also minus Vmin and also minus Vmax over here. Okay, so how much is Vmax? Vmax is equal to Vmax is equal to Vc plus Vm, peak value. Okay, and Vmin is equal to Vc minus Vm. Okay, so if you calculate this one, 8.6313, because we get the Vm is 7.071. Okay, so this is actually equal to 8. So 8.6313 plus this one. This one is, both of these is Vm actually 7.07. So we get 15.70. Okay, so over here is 15.7023. Okay, and the Vmin is 1.56. 1.56. Here is minus 15.7023. Sorry. So minus 1.56 minus Vmin. This is minus Vmin, and over here is minus Vmax, minus 15.7023. So the graph is actually what they call is a reflected. It's like a reflection. The positive and negative is like a reflection. So you have the positive side and also the negative side. Okay, so when you want to draw, make sure you draw correctly and then you label correctly. So in this case, for the waveform, okay, for the waveform of AM, you need to draw correctly and then you label the axis and you label the maximum and minimum. That's enough. Okay, so dalam exam, in the exam, make sure you draw correctly, then you label correctly for the axis, y-axis and x-axis, and you label the maximum and minimum value. Of course, you need to find the value. Don't just put Vmax, Vmin in the label. Don't just put Vmax and Vmin over here. You need to put the value. Okay, jangan hanya letak variable Vmax and Vmin. You need to put the value because you can find the values. Okay, unless you cannot find the values, then you need to put variable Vmax and Vmin. Okay, so do you have question about this example? If you have question, you don't understand, I can explain again what you don't understand. Okay, kalau ada soalan boleh tanya. You are most welcome to ask question. Boleh? Student, are you still there? Anybody can respond?
Clear, everything
okay.
Clear.
Okay, so no question. So I move to the next example. Okay. So this is next example. This is the next topic, which is modulation by several sine waves. So how to calculate the total power if we have more than one input message? Okay. So previously you learned that you only have a VCT, which is VC sine 2 pi FCT, the carrier, and you learned that you already have VMT equal to VM sine 2 pi FMT. Okay, so what if we have more than one VM? What if? Okay, for example, I have a VM1 equal to VM 1 sine 2 pi FM1T. I have another one, VM2 T, which is equal to VM2 sine 2 pi FM2 until n. Okay, until n. So how to calculate the modulation index and also the total power? Okay, so if we draw the picture, I mean for the transmitter, okay, the transmitter, that means in the transmitter we have carrier, okay, and we have more than one input, several inputs, okay, and we have only one carrier, and then we transmit the AM. So therefore the total voltage, okay, is equal to square root of V1 square or plus V2 square plus V3 square. Okay, and we can calculate the modulation index by V total over Vc, which is equal to square root of, so we divide each of it with Vc. So V1 over Vc square plus V2 over Vc square plus V3 over Vc square. So this is actually equal to modulation index of the first message signal, modulation index of the second message signal, and modulation index for the third message signal until modulation index of the n input signal. Okay, so you see that we calculate the square root of modulation index for each input versus the carrier. Okay, m1 plus m2, so this is m1 square because we do square, so m1 square, m2 square, m3 square until mn square. Okay, then we do the square root. Okay, so if you see from here, we can calculate the modulation index, total modulation index equal to m1 square plus m2 square plus m3 square until mn square, and then you can do the square root. Okay, so from here we can calculate the total power for the double sideband full carrier equal to PC multiplied with 1 plus m total square, total modulation index square, divide with 2. Okay, so previously for the single input, if you remember, we use like this, PC 1 plus m square over 2. But since we have many inputs, that means we need to find the total modulation index. Okay, so how does the multiple input equation looks like? Macam mana bentuk equation untuk multiple input? Okay, if you see from the previous question bank, okay, if you see from the previous semester's question banks, you see that we have asked this kind of question in the previous semester. Pernah ditanya beberapa kali, more than once. Okay, so if you see from the previous semester's question, okay, what we give is like this. So previously we give the carrier, okay, which is we give the value Vc sine 2 pi fct. Okay, we give the value, but this is just to give you to show you what kind of question is it like. Okay, and we give the value, we give the equation for signal, which is something like this. M of t equal to Vm1 sine 2 pi Fm1 plus Vm2 sine 2 pi Fm2t plus Vm3 plus Vm3 sine 2 pi Fm3 t. Okay, in the previous semester we have asked this kind of question. Okay, so but in that question, of course, we give the values. We give the value of each parameter. So here for this example, I just give you the variables. Okay, so you see that from this kind of question, what we can extract is that okay, we know how much is Vc, we know how much is carrier frequency, we know Vm1, we know frequency of first message, we know Vm2, frequency of the second modulating signal, Vm3, and also the Fm3. From here we can calculate the total modulation index, which is this one. Okay, so modulation index is equal to for this one, you see that for M1 is equal to Vm1 over Vc, M2 is equal to Vm2 over Vc, M3 is equal to Vm3 over Vc. Okay, so you can calculate each of the M Okay, once you get M and then you calculate the total modulation index, then you can find the total power. This one, total power. Okay, so carrier, of course, carrier is Vc square over 2R. M total from this calculations from the quadratic equations, and then we can calculate the total modulation index, so we get the total power. Okay, so before we proceed, maybe I want to explain further. Okay, maybe I want to explain further how does the frequency spectrum looks like. Okay, so remember that first we have okay, I change to red color. Okay, so I draw this one. Remember my favorite picture like this. Previously we learned that we have only single input message, which is VCT and also VMT. Okay, and from here we so I draw the spectrum. Okay, so I will show you. Okay, I will show you. So from single input message, remember for the double sideband full carrier we get wait, I change color. Okay, so this is this. Okay, so we get double sideband full carrier. Okay, remember this one. If we have single input message, modulate with the carrier and produce double sideband full carrier, so the spectrum looks like this. Okay, so remember that this is Fc, this is Fc plus Fm, this is Fc minus Fm, and if you remember, this is this is Vc. Okay, and this is Vm over 2. Okay, so now what if, okay, sorry, this is V versus F. What if we have more than one input? So what happened? Okay, so what happened is that each input will produce two sideband, upper and lower, for each input. So imagine if you have 3 input, that means you're going to have 6 sidebands, 3 upper and 3 lower. Okay, so what happened is that it's going to be like this. Okay, apa yang berlaku adalah seperti ini. Okay, so I redraw again. Wait, so I make it bigger. It's something like this, something like this. Okay, so this is for the first input, and if we have another input, so maybe I can use another color. Sorry, for the second input. Okay, what happened is that it's gonna be located over here. Second input, so this is located at Fc plus Fc plus Fm2. Okay, so this is previously is Fm1, so Fm2. Similar, this was located at Fc minus Fm2. And the third input, maybe I can use purple color. Okay, so the third input is located at Fc plus Fm3, and located at here. Okay, Fc minus Fm3. That's the location. Okay, what about the amplitude? Okay, so the amplitude here is Vm3 over 2. Okay, and then what green color, sorry, So green color, so this is Vm2 over 2, this is Vm2 over 2, and then black color, sorry, so this is Vm1 over 2, this is Vm1. Okay, so for double sideband full carrier, each input will produce two output, lower and upper sideband. Okay, lower and upper sideband. So imagine if you have many input, so the spectrum will be much wider. Okay, kalau kita ada banyak input, maka dia punya spektrum itu akan lebih lebar. Okay, so this is the waveform. Okay, and what about sorry, this is the spectrum. What about the waveform? So the waveform will looks similar actually. Okay, the waveform will look similar, only the input message is different. So what you need to know only for the spectrum. Okay, normally we ask for the spectrum. For the waveform is quite similar with the single input, because the information within the envelope is contains more than one information. Okay. Okay, so in order to see this kind of example, you can for more input, you can see from the previous semester question bank. Okay, so back to the topic. Okay, so I explain another thing. Sorry, I explain related with the previous question. Okay, so we go back to this topic now. Okay, so okay. So back to here, okay, back to this equation. Okay, so previously we have seen this, okay, and so that means the total power can also be changed into current equation. Okay, for example, here total power can be change into equation based on total current equal to carrier current multiplied with R. Okay, so IT square multiplied with R equal to IC square multiplied R in bracket 1 plus M square over 2. And if you rearrange the equation, you can actually cancel out the R value, so it becomes IT over IC square root of equal to square root of 1 plus M square over 2. So this is for the single input. If you have multiple input, you just need to change the M total. This is for the double sideband full carrier. Okay, each sideband produce two output. Each input produce two sidebands at the output. Okay, setiap input message menghasilkan dua sideband. Okay, a pair of sideband at the output. Example 3.5 about the antenna about the current related to the current. So the antenna of an AM transmitter is 8 ampere when only the carrier is sent. But it increased to 8.93 when the carrier is modulated by a single sine wave. Find the percentage modulation and the antenna current when the percentage of the modulation changed to 0.8. So how to do this? So the question asks two questions. The first one, find this one based on the given value. Find the percentage modulation index. Okay, so if you see from this question, okay, first of all, you are given the antenna current when there is no input signal. So that means if you draw like this, okay, so when there is no input signal, there's only the carrier signal. without the input. So that means this is actually referring to the I current, sorry, I carrier. Okay, I carrier is 8 ampere. But when there is an input, so it will modulate the carrier and produce higher value of output current. Okay, so what happened here is that the output current is actually the total current when we have the input. Okay, because modulation happens. Okay, so that means here is IC, this one is I total. Okay, IC and I total. So therefore, okay, therefore you can calculate the modulation index, okay, based on the equation of this one, P total equal to PC, okay, 1 plus m square over 2, okay, and this one is IT over IC equal to square root of 1 plus m square over 2, this one, okay, so square root of 1 plus m square over 2, okay. So if you divide this one, I total is equal to 8.93 divided with 8. So this is equal to square root of 1 plus m square over 2. Okay. So this one is equal to so therefore 1 plus m square over 2, this is equal to boleh cuba calculator, use your calculator, 8.93 divided with 8, so this is 1.11 this is 1 point, sorry, you need to do the quadratic, sorry. So 8.93 divide with 8 and then you do square of answer. So you get 1.24. Okay, 1.246. Okay, 1.246 if you do the power of 2. Okay, 8.93 divided with 8 power of 2. Okay, so 8.93 divide 8 and then power of 2 equal to 9. Okay, so okay, 1.246. okay, so therefore this one m over 2, so m over 2, m square over 2 is equal to 0.246, okay, so m square is equal to 2 times 0.246, so you get 492, 0.492, so m is equal to square root of answer 0.701, 0.701. Okay, so this one actually the answer is wrong, so I need to correct this one. So for the first question they asked for the percent, so that means for percent, so m for percent, so that means this is 0.701 multiplied with 100%, so you get 70.1, 70.1%, 70.1%, okay, 70.1% if you multiply it with 100%. So because the question asks the percentage, so we need to multiply it with 100, so 70.1%. okay, so that's the first question. Okay, find the percentage of the modulation. Okay, and the antenna current. Okay, so the second question asks Okay, the second question, because this is n, so that means there's another question. The second question asks, find the antenna current when the percentage modulation change, okay, to 0.8. So the antenna current is actually the current supplied to the antenna, and now the modulation index is increased, okay, from 0.701 increased to 0.8. Now, so modulation index increased to 0.8. How much is the total current? So in this case, we must assume that the carrier current is the same. Okay, we must assume that the carrier current is the same. Okay, so therefore, you can use the equations. So this is wrong. So therefore you can use this, IT is equal to IC 1 plus m square over 2. Okay, so we want to find the total current. The current supplied to the antenna is the total current. So we assume that the carrier current is still the same. Okay, we still use the same carrier, okay, which is 8. Okay, multiplied with 1 plus, now the modulation index is 0.8. Okay, modulation index has been increased 0.8. So therefore we get, how much is this? Try use your calculator. 0.8 square divided with 2 plus 1 multiplied with 8. So we get 10.56. Okay, 10.56 ampere. Okay, 0.8 multiplied square by with 2, so plus 1 multiplied with 8, so 10.56 ampere. So again, this is wrong. Okay, okay, so do you have any this is supposed to be 10.56. Okay, okay, so any question about this? Ada soalan nak tanya?
No, Doctor.
Okay.
Doctor?
Yeah.
Why we need to find the modulation since we already know that it will increase up to 0.8?
Sorry, could you please repeat again?
Why we need to find the modulation that 70%? Since we already know from the question that the modulation will change up to 0.8. So in the calculation, we only use 0.8, right? Not 0.7.
Okay. Because there are two questions here. Okay, because there are two questions here. You see that the first question asks to find the percentage of modulation given from the given values. So from the given values 8 and 8.93, we need to find the percentage modulation M. Okay, and then you see that the question has AND. That means the second question asks find the current to the antenna, which is the total current, if the modulation index become 0.8. That means this question actually want to show you that what happened to the total current if we increase the modulation index. Okay, so the answer, my answer is that you need to find two things. First, you need to find the modulation index based on the given value. Then you need to find the total current if we increase the modulation index. So nampak sebenarnya soalan ini ada dua sebenarnya. Yang pertama, cari percentage modulation index based on the given currents. Then the question asks you to find the total current, which is the current to the antenna, if we increase the modulation index to become 0.8. Boleh ya?
Okay, boleh.
Okay.
So let's say if the second question does not ask us to change the percentage of the modulation to 0.8, so we only take the 0.7 as the modulation into the next
So
solution.
that means sorry so that means if let's say there's no this question, the second question is not given, so you just need to find the first one, which is 0.701, or in percentage 70.1%.
Okay, Doctor.
Okay, any more question? Okay, if there's no question, I move to the next topic. Okay, tak ada soalan So if there's no more question, if you would still want to ask, no problem, you can ask me question. Kalau ada? Tak ada Okay.
Tak ada.
Okay. So I move to the next topic. So the next topic is about the other types of AM. Remember, AM has many types. Okay, the first type that you learn is about double sideband full carrier. That's the oldest type of AM. Okay, but there are other type of AM, which is what we call as double sideband suppressed carrier. Okay, double sideband reduced carrier, single sideband, and also the vestigial sideband. Okay, so if we want to draw the spectrum, okay, I will show you. For double sideband suppressed carrier, how does the spectrum looks like? Okay, so the term suppressed carrier means that the carrier component has been suppressed completely. Okay, so it becomes like this. So there's no, here is a carrier FC, over here is, let's say, FC plus FM. Sorry, mungkin saya kena, sorry, maybe I need to draw a bit below here. Wait. So I will draw so that you can see. So okay, I just want to show the spectrum. How does the spectrum looks like? So V versus F. Okay, so you see that here is F. This is actually at the carrier. So this is FC plus. This is OFC. Okay, so for this one, double sideband suppressed carrier, what happened is that the carrier component has been suppressed, so there's no carrier component, only the sidebands component. Okay, the carrier component has been suppressed completely. Okay, but how much is the value for the amplitude of the sidebands? Based on the equation. Remember students, remember the value of the amplitude of the sideband is not Vm over 2. Okay, so the value here is not so here is VLSB and VLSB and VUSB. Okay, so VLSB and VUSB in this case is not equal to Vm over 2. So you need to be careful. So how can we determine the VLSB and VUSB? So in order to determine the value, we need to define the equation first. Then we can know how much is VLSB and VUSB. Without the equation, we don't know how to calculate the VLSB. Okay, so be careful. Okay, so when we go to the other type of AM, the equation will be different. Okay, so the spectrum also will be different. Okay, so based on the previous semester experience, when we gave the question about double sideband suppressed carrier, student did careless mistake. They assume that the VUSB and VLSB is equal to VM/2, which is wrong. Okay, it is not equal to the double sideband full carrier. Okay, and then what for double sideband suppressed carrier? Okay, so double sideband reduced carrier. So that means this is for reduced carrier. This is Fc minus Fm. So reduced carrier, that means the carrier has been reduced. Okay, reduced to certain percentage. Okay, so this is Fc plus Fm. Okay, so the carrier has been reduced actually from the original amplitude become reduced to certain percentage depending on the application. Okay, so the carrier component reduced to certain percentage. And then what? Single sideband SSB. SSB contains two types. SSB with carrier. Okay, SSB with carrier and also SSB without carrier. Okay, so how can we draw the SSB? SSB means that the sideband is single. Okay, so for single sideband, you can choose either lower sideband or upper sideband. Okay, you can choose either lower sideband or upper sideband. Okay, so for example, this is Fc, this is Fc plus Fm, this is Fc minus Fm. Okay, so for example, this is single sideband with carrier. So if this is single sideband with carrier, that means we have the carrier component and we have either one of the sideband. For example, I choose upper sideband like this. Okay, so this is single sideband with carrier. Okay, using the upper sideband. There's also another one, what we call as single sideband without carrier. Okay, if this is without carrier, that means there's no carrier component. Tidak ada carrier component. So this is Fc. Okay, so no carrier component and only one sideband. So for example, I choose upper sideband, for example. So there's no carrier component, there's no lower sideband. Remember, for the sideband, you can choose either one, lower or upper sideband. Okay, boleh pilih antara lower ataupun upper sideband. And SSB contains two types, with carrier and without carrier. Okay, and then vestigial sideband, you're gonna see later that vestigial sideband. Okay, for vestigial sideband, we have vestigial sideband is like double sideband full carrier. The only difference is that the amplitude and also the length, the distance here. So this is, for example, here. Okay, it is not the same. The amplitude is not the same, and also the distance from the carrier is not the same. Okay, you're gonna see later about this. So vestigial sideband is used for the TV broadcasting, which consists of video signal and also the audio signal. Okay, so we're gonna see one by one. Okay, so double sideband suppressed carrier. Okay, so double sideband suppressed carrier, so this is from the literature books. You see that this is the power calculation is equal to limit 1 over t from minus t over 2 until t over 2 v square dsbsc dt. So there is actually r, actually there's r over here, but r is assumed to be equal to unity, so that's why there's no r component over here. Remember, the equation for power is still the same from previous, now, and forever. Okay, so it is still in this case it is based on the RMS value, so Vrms square over r. Okay, so r is equal to unity, so that's why there's no r component in this case. Okay, so you don't need to memorize this equation, tidak perlu hafal. Okay, don't need to memorize. So you see that here this one is V dsBSC. So V dsBSC, so so Vc square Vmt square cos 2 pi fct. Okay, so this is actually supposed to be cos square, so because the equation is Vc Vmt cos 2 pi fct. Okay, so if you do based on the trigonometry identity, okay, this cos square can be defined as 1 over 2 1 plus cos 2a, so becomes 4 pi. So this is based on the trigonometry identity, divide with 2. Okay, so 1 over 2 in bracket 1 plus cos 2 times of fc becomes 4. So 4 pi fct. Okay, and it has put outside the voltage carrier because this is a constant value, so we get these parameters. Okay, and according to this equation, okay, it is said that we can cancel out this component. Okay, because this component, if multiplied with Vm square, it will produce a very small values which is insignificant. Okay, and it can be neglected. Okay, so therefore it only contains Vmt square, okay, which is the produce the power of the modulating signal. Okay, so that's why Vc square over 2 pm. So you don't need to memorize this. I will show you how to get this power. Okay, remember, total power is equal to PLSB plus PUSB. There's no carrier component because the carrier component has been suppressed completely. Okay, so you don't need to memorize this. We're gonna show a few examples later. Okay, so this is the waveform of double sideband suppressed carrier. Okay, so you see from here, the above part here is the carrier signal. Over here is the modulating signal Vmt. Here is the waveform for the double sideband suppressed carrier. Okay, and the graph below is the frequency spectrum. So you see that from the frequency spectrum, there's no carrier component, only the LSB and also the USB. Okay, the carrier has been suppressed completely. And then what? If you see from the waveform, you're gonna see there's a significant change over here. This is what we call as 180-degree phase shift. Okay, 180-degree phase shift. Okay, So how can we draw this waveform during the exam? Macam mana nak lukis waveform ini ketika exam? Nah, so how to draw? Okay, because when you want to draw, you need to show the phase shift as well. Okay, so I will teach you how to draw the waveform. First, when you draw the waveform, you can do like this. Yeah. Okay, so when you want to draw, first you draw the axis. Okay, you draw the axis V versus F. So V versus F. Okay, sorry, V versus T. Sorry, this is a waveform. V versus time. Sorry, this is a time domain. This is a waveform. So that means you need to draw V versus time. And then what? You can draw the imaginary line. Okay, you can draw the imaginary line like this, like a sine wave, like this. Okay, like a sine wave, and another sine wave inverse like this. Okay, this is imaginary line. Okay, and then what? Then you can draw. Okay, so perhatikan so see how I draw it. So after I draw the imaginary line, so the imaginary line is like a sine wave and also an inverse sine wave. So after I get this imaginary line, so this is my reference line, so that I can do the I can draw the ripples like this. Okay, and then what? Sorry, wait. I repeat again. So you can draw like this. So don't use ruler, wasting time. So instead of going down, okay, what happened is that the signal will goes up. It becomes inverse. So this is what we call as a 180-degree phase shift. Okay, I repeat again, because we have asked this a few times in the previous exam, how to draw this one. So after I draw the imaginary line, I can draw the ripples like this. I can draw the wave. Okay, so instead of going down, it becomes inverse. Okay, I go up. Okay, so you need to show that significant changes. Okay, so it doesn't mean like this, it can be like this, so it doesn't mean go up like that, so that means you just need to change the position. Okay, for example, I do like this, for example. Sorry, jap. Now instead of going up, you can inverse the wave, come to go down like this. You can also do like this. Okay. The thing is, we need to show the changes over here 180-degree phase shift. Okay, that's it. So here again, this is Vmax. Okay. So you don't need to plot this one. Is never mind. We don't want to see this one actually. So you can say this is the Vmax and this is the Vmin. Okay. Sorry, this is a minus Vmax. Sorry. Okay. That's it. Finish. Okay. Advantage of double sideband suppressed carrier compared to the AM. So AM here, okay, AM here is referring to the double sideband full carrier. This is actually double sideband full carrier. Okay. So what's the difference? Power conservation can be allocated to both sides, longer distance, easy to generate. So it is said that, okay, theoretically, okay, when you kejap. I think my stylus has problem, is it? Okay, so theoretically it is said that if we suppress the carrier, okay, if we suppress the carrier component, the power will be allocated to the sideband, theoretically. Okay, as if when you suppress the carrier power, it is divided to the upper and lower sideband. That means the power is distributed to the upper and lower sideband. Okay, when you suppress the carrier power, the power is distributed to the upper and lower sideband. That means the upper and lower sideband amplitude becomes higher. How is it possible like that? Okay, so mathematically it is true. Okay, I will show you about that. Okay, mathematically. So mathematically, you will see that the amplitude of the upper and lower sideband becomes higher compared to the double sideband full carrier. Okay, so this is Fc plus Fm, this is Fc minus Fm. Okay, so how is it possible? We're going to see about the equation later, which shows that the peak amplitude of the sideband becomes higher. So that's why for double sideband suppressed carrier, it is power conservation because we suppress the carrier power completely. There's no carrier component. Carrier component does not carry any information, so we manage to remove the majority of the power at the carrier. We remove it, and it is not removed completely actually because we divide to the sideband theoretically. Okay, so power conservation, so we reduce the amount of power that we use for transmission. Okay, we reduce because we remove the carrier component. And then easy to generate. And then rarely to disadvantage, rarely to used. Okay, rarely used because the signal is difficult to recover at the receiver, require carrier insertion and complex circuitries. So the circuit at the receiver is more complex compared to the double sideband full carrier. It takes the same amount of bandwidth, not efficient for some of the application. Okay, so the bandwidth is still the same. Okay, the bandwidth is still the same, which is equal to 2FM, and not efficient for some application. Okay, some other application is good. Okay, And then what? Single sideband. So in double double sideband, information is transmitted twice, each in one sideband. For double sideband suppressed carrier and also for the full carrier, we transmit the signal as if we transmit twice, because the signal is the information is duplicated in the lower and upper sideband. Okay, so one sideband may be suppressed, okay, if we use a single sideband suppressed carrier. So in the single sideband, when no info or modulating signal is present, no RF is transmitted. Okay, so in this SSB, when there is no input, there's no RF signal is transmitted. So if we use a single sideband without carrier, okay, so if there's no input, we are not transmitting anything. Okay, different from the double sideband or single sideband with carrier. So when there's no input, we might transmit a carrier signal only, okay, which is the RF. RF here referring to the carrier signal. Okay, because single sideband consists of two types, with carrier and without the carrier. In standard AM here is the double sideband full carrier. Carrier is still transmitted even though it may not be modulated. Okay, in double sideband full carrier, we are still transmitting the carrier even though there's no input message. Okay, and this is the waveform of the single sideband. This is single sideband with carrier. So you see that here we have the carrier signal, modulating signal, and this is the waveform for the SSB with carrier. And then this is the power spectrum for the SSB with carrier. So you see that here we have the carrier component FC. This is FC plus FM. So this is actually single sideband using the upper sideband. Okay, so if you see from here, how much is the bandwidth actually? So the bandwidth is half of the double sideband. Okay, the bandwidth is only FM. Okay, bandwidth is equal to FM, only single. Okay, single side. Okay, and then this is single sideband without carrier. So you see that the upper one is carrier and then modulating signal, and this is the signal for the single sideband without carrier, and this is the power spectrum. Okay, so power spectrum here use the upper sideband. So there's no carrier component, only the upper sideband. Okay, and there's also no lower sideband. There's no FC minus FM. There's no lower sideband. Okay, so you see that the peak amplitude here is not equal to the double sideband. You will see later when we use a single sideband without carrier, the amplitude of the sideband is larger. Okay, so when we suppress the carrier, theoretically the power will be allocated, will be distributed to the sideband. So the sideband amplitude becomes higher theoretically. Okay, it can be shown through the mathematical equations later. Okay, so in this case you see that there's no carrier component, only the upper sideband. So in this case the bandwidth is equal to FM. Okay, the distance from the carrier. Okay, the distance from the carrier, which is FM. Example, this one. Okay, for 100 watt of available power in the sidebands. Okay, so you're gonna see a few examples, this one and the next examples, all about calculation. So I hope that you are not feeling tired, okay, because we will do a lot of calculation today, okay, for the examples. Okay, So example 2.9, for 100 watt of total available power in the sidebands. Okay, so 100 watt of total power, that means this is P total. Okay, compare the power in the sidebands when the modulation is standard AM. Standard AM is double sideband full carrier with modulation index 100% versus double sideband suppressed carrier designed when 90% only of the carrier power is suppressed. How many times greater is the sideband power in the suppressed carrier case? So what is this about? So actually initially like this, we have the double sideband full carrier. Okay, the question is like this actually. Okay, we have double sideband full carrier. Okay, Vsb Fc, double sideband full carrier, and then this one has a modulation index m equal to 1, and we need to compare with double sideband suppressed carrier. Okay, when 90% of the carrier has been suppressed. Okay, suppressed 90%, so the remaining is 10% only. Okay, so theoretically, as I mentioned before, that when we suppress the carrier component, it will be the power or the voltage amplitude will be distributed to the upper and lower sideband. So the upper and lower sideband amplitude becomes higher theoretically. Okay, so you see that for the double sideband full carrier during the 100% during the modulation index 100%, or during the ideal case. Okay, so during the ideal case, you see that the total power, so this is actually P small t, this is actually P small t, subscript of T, this is also subscript of C, so PC, this is m square over 2, m square over 2, so this is subscript of C, so that means PT is equal to 3 over 2 of PC. Okay, and PC is equal to PC is equal to 2 over 3 of P total. Okay, so this is taken from the general equation of power, P total equal to PC 1 plus m square over 2. Okay, from here, and using m equal to 1. Okay, so during the ideal case here, carrier power is 2 over 3 from the total, and total power is 100 watt. That means 2 over 3 is equal to 66.7 watt. And the sideband power, both of it, lower and upper, is equal to 100 minus 66.7, which is 33.3 watt for both upper and the lower sideband. Okay, so up to here is for the double sideband full carrier. Okay, double sideband full carrier. So what if so let's see what happened to the reduced carrier. Okay, so for the reduced carrier, it is said that when we reduce, the power will be distributed to the sideband power. Okay, so how much is 90%? That means we remove 90%. We remove 90% from the carrier power, so the remaining is 10 watt only for the 90% from the 66.7 has been suppressed. Okay, so 90% from the 66.7 of the carrier power is equal to 60 watt. So this 60 watt is reduced in the suppressed carrier system. Okay, but theoretically this 60 watt is not it's not removed completely from the system. Okay, it is actually distributed to the sideband. So 60% distributed to the sideband. That means if we use a suppressed carrier, we can increase the sideband power from initially 33.3 watt plus becomes higher plus another 60 watt. So it becomes 93.3 watt in the suppressed carrier case. Okay, this is double sideband suppressed carrier. Okay, if we use double sideband suppressed carrier, we suppress 90%. That 90% distribute to the upper and lower sideband. So the upper and lower sideband power becomes 93.3. Okay, so 33.3 plus 60 watts, so become 93.3. Okay, so this answer the first question. Okay, the first question asks compare the power. Okay, and the second question asks how many times greater is the sideband power in the suppressed carrier case. How many times greater? So that means we need to do the ratio of a new power sideband divide with old power sideband. Okay, so PSB new 93.3 watt divide with 33.3 watt, so we get 2.8. 2.8 we can express in terms of decibel, so 10 log 2.8 we get 4.5 dB. Okay, 4.5 dB. Okay, this means that in AM information info transmitted only 33.3%, but in the double sideband suppressed carrier about 93.3% belong to the sideband power. Okay, how does it get a 93.3? Because the total is 100 watt. Okay, total is 100 watt. Okay, so from the total 100 watt, 93.3 watt belongs to the sideband, which is good. And the carrier has been suppressed for 90%. Okay, so you might wonder, how come when we reduce the power of the carrier, it is distributed to the upper and lower sideband? Okay, so in order to answer that question, you need to see the mathematical equation. From there you will see, theoretically, when we suppressed the carrier component, it will be distributed to the upper and lower sideband. So the upper and lower sideband amplitude becomes higher. Okay, so you will see later in another example how can we achieve this in another examples. Okay, so if you have question, do you have question about this, you can ask. Otherwise I will move to the next slide. Okay, kalau ada soalan boleh tanya. Okay, so if you don't have question, I will move to the next. So this example is the same. So this example is the same. You can read on your own. This is the same as 2.9. Okay. Advantages of single sideband compared to AM, compared to double sideband full carrier. Okay. So single sideband versus double sideband full carrier. What is the difference? In terms of power, it is power conservation, because we reduce the either one of the sideband power, and we can also reduce the carrier power as well for the single sideband without carrier. So it's conserve a lot of power for the transmission. Okay. So then bandwidth conservation. So in single sideband, the bandwidth is half of the double sideband full carrier. Okay, which is more efficient. spectrum efficient. Okay, spectrum efficient. It allows more signal to be transmitted in the same frequency range, less interference with between signals, and then less fading. So fading is multiple attenuations that happens when the signal transmitted from the transmitter to the receiver. So the multiple fading, the multiple attenuation process is what we call as the fading. Okay, in terms of fading, that means less fading. That means the signal is stronger enough to reach from the transmitter to the receiver. So that means when the receiver receives the signal, it is much better. It has a higher power. Okay, the received signal power is higher if we using the single sideband compared if we use the double sideband full carrier. Double sideband full carrier, the fading is higher. Okay, and then noise reduction, because the bandwidth is less. So why is this possible? Why the noise power reduce? Remember, if you have learned my video, noise power is equal to KTB, the Boltzmann constant multiplied with the temperature in Kelvin multiplied with the bandwidth. So if we reduce the bandwidth, we will reduce the noise power. Okay, so this you learn in chapter 2. Okay, about this one. Disadvantage of SSB compared to AM. Disadvantage of single sideband compared to double sideband full carrier. So what is the disadvantage? So complex receiver can use envelope detection technique unless carrier is regenerated, added to cost, complexity and size. So in terms of a receiver system design, it is more complex and more expensive compared to the double sideband full carrier, and it will cause tuning difficulties, require more complex and precise tuning. It needs more accurate, complex and expensive tuning circuit. Okay, Vestigial Sideband Vsb. Okay, so Vestigial Sideband is used for the TV broadcasting. Okay, so carrier and one complete sideband are transmitted, but only small vestige part of the second sideband is transmitted. So this is used for the TV broadcasting. So you see that the sideband is not equal. Okay, the sideband is not equal. One is bigger, one is smaller. Okay, so this is used in the TV broadcasting, which consists of video and audio signal. Okay, so audio signal is frequency modulated. Video signal or picture signal is amplitude modulated. So it consists of two modulation types, amplitude modulated and frequency modulated. So video signal typically contains frequency as high as 4.2 megahertz to 4.2 megahertz to 8.4 if fully double sideband full carrier. So if fully double sideband becomes twice, 8.2 megahertz. So excessive amount of bandwidth wasteful because not all of it required to reliably transmit a TV signal. So vestigial sideband is not a fully double sideband. It's not a fully double sideband. It means that the distance between a carrier and the sideband is not double. It's not 2 FM. Okay, so one of the sideband is further away from the carrier compared to the other. Okay, so this vestigial sideband try to reduce the bandwidth. Okay, it tries to reduce the bandwidth. So the bandwidth is actually not equal to 2 FM. Okay, so they play around with the distance of the spectrum. Okay, because if we multiply with 2, Okay, because the video frequency needs a high frequency. So if we multiply with 2, the video frequency becomes much bigger bandwidth, which is not efficient for transmission. So that's why vestigial sideband try to reduce the bandwidth compared to the double sideband full carrier. Okay. So advantage of VSB compared to single sideband, design of sideband filter is more simplified. No need sharp cut-off filter. Okay. Improve low frequency response. Okay. So these are the advantage. So what is the disadvantage? The disadvantage is that the bandwidth is still bigger. Okay, bandwidth is higher in the vestigial sideband compared to the single sideband. Single sideband, the bandwidth is equal to FM. So for the vestigial sideband, it is more than FM. Okay. Okay, and then so here is actually this one is separate actually. So factors to consider when choosing the amplitude modulation. So when you want to choose which AM you want to choose actually. Okay, when you want to choose a double sideband full carrier, suppressed carrier, reduced carrier, single sideband or vestigial sideband, there are a few factors that you can consider in order to choose the best possible AM type. Okay, for example, bandwidth allocation. If you need smaller bandwidth, you cannot use double sideband full carrier, you need to use single sideband. Power, if you want to reduce the amount of power, you can use suppressed carrier of single sideband. Okay, signal to noise ratio SNR. If you want to transmit signal with higher SNR, okay, SNR, we need SNR to be as high as possible. In order to increase the SNR, we need to reduce the noise level, noise power. So in order to reduce the noise power, we need to find we need to produce signal that has a lower noise power. For example, like the single sideband. Okay, because noise power is related to the bandwidth. Okay, complexity, if we want a less complex circuit, we can use double sideband full carrier. If you want system that has a low cost, we can use a double sideband full carrier. Distance for transmission, we need to use a single sideband with carrier or without the carrier. Okay, so even for the double sideband suppressed carrier also, we have the higher amplitude of the sideband. So the distance, we need to choose a modulation type that produce higher sideband power. Okay, we need to choose the modulation type that produce higher sideband power. So maybe it is a suppressed carrier or single sideband okay, compared to the double sideband full carrier. And I want to show you about this picture for the second picture, the first and the second, this one. This is for the vestigial sideband. So if you see from here, vestigial sideband, the power, I mean the amplitude power, okay, for the upper sideband is larger compared to the power of the lower sideband. Okay, in terms of amplitude, the upper sideband is bigger compared to the lower sideband because upper sideband is allocated for the video transmission, lower sideband is allocated for the audio transmission. Remember, TV broadcasting consists of video and audio. Okay, so we need larger bandwidth for the video transmission and smaller bandwidth for the audio transmission, because audio does not require larger bandwidth. Audio just needs small bandwidth. Okay, And then in terms of the distance or the bandwidth, you see that this is larger than the lower sideband. Okay, because in terms of power, video transmission need higher power and also need bigger bandwidth compared to the audio signal. Okay, so in vestigial it is divided for audio and video transmission. Okay. Okay, so now we move to the modulator circuit. Okay, modulator circuit. Okay, if you see the modulator circuit, so modulator is part of transmitter. Okay, modulator ini adalah sebahagian daripada transmitter. Okay. So amplitude modulation voltage is produced by a circuit that can multiply the carrier by the modulating signal and then add the carrier. So we're going to see about this based on the equation. Product of the carrier and modulating signal can be generated by applying both signal to the non-linear components such as diode. Okay, this is in the circuit. Intermodulation product, third, fourth and higher harmonics are produced by diodes and transistor. Of course, during the modulation process, you're going to produce intermodulation products. Okay, this is what you learned during the chapter 2 about the intermodulation distortion. Okay, which produce the harmonics. Okay, so tuned circuits filter out the modulating signal and carrier harmonics, leaving only the carrier and the sideband. So in order to remove the harmonics are short amplitude signals that produce through the modulation process. So we need to remove this by using the filtering circuit, or what we call as the tuned circuit filter. Okay, so this is the block diagram for the AM modulator. Okay, so AM modulator, if you see that here, it involves a multiplication and addition process mathematically. Okay, remember that we have a Vc sine 2 pi Fc. This is actually taken from the envelope. Wait, So this is a Vc sine 2 pi plus Vm sine. Okay, so there's a multiplication process and also the addition process. Okay, so there are two types of amplitude modulators: low level modulator and high level modulator. So there are two types. Okay, low level modulator generates AM signal with small signal and must be amplified before transmission. Low level modulator produce AM with small amplitude, and before transmission we need to amplify it using the amplifier. Okay, that means the VAM produced here is lower and needs to be amplified. That means we need to add additional amplifiers. Okay, additional amplifiers to increase the amplitude before transmission. Okay, high level modulators produce AM at high power level, usually in the final amplifier stage of transmitter. So high level means that the modulator produce high amplitude of signal, and this signal is suitable for transmission directly. Okay. Okay, low level. Okay, the first one, low level amplitude modulator, which is the first one is diode modulator with tuned circuit filter. Okay, so in the previous semester we have asked this question. Okay, not to draw the circuit. We are not asking about circuit. We ask you to draw the waveform at certain point of the circuit. Okay, so you see that this circuit consists of two inputs. One is a modulating signal and another one is a carrier connected to the resistors and then connected to the diode. So remember, diode allows current to flow in one direction only, okay, and it prevents reverse bias. Okay, so it only allows current to flow in one direction only and block the reverse bias. Okay, so what happened during the forward bias? Okay, during the forward bias, we have another one here, what we call as a tank circuit, LC tank circuit. So this LC tank circuit is like a fast charging battery. Okay, this is like a fast charging battery. So this tank circuit acts as a fast charging battery. So during the forward bias of the diode, this tank circuit will charging. Okay, and during the reverse bias, okay, current cannot flow in this direction. Okay, current cannot flow in this direction. So what happened is that the waveform will be cut off. Okay, in order to compensate that cut off during the reverse bias, this LC tank circuit will discharge. Okay, it will discharge during the reverse bias. During the forward bias, it will charging. During the reverse bias, it will discharge. Okay, so if you see the this graph, okay, we have asked this graph in the previous test and final exam in the previous semester. Okay, so the question is like this. The question asks, sketch the waveform at these 3 points. Point A, okay, point B, over here, point B, and point C over here. Okay, sketch the waveform. Okay, so at point A, both modulating signal and carrier signal are mixed together. Okay, so what happened? Okay, so you see that the first picture here is the modulating signal or the message signal. The second waveform here is the carrier signal, and this is the signal that combine both carrier and modulating signal. Okay, so at point A, this is at point A, both carrier and modulating signal are combined. So combine is a mixing, mixed together. So what happened is that the carrier signal follows the shape of the modulating signal. Okay, this is what we call as combine. Okay, this is not modulation, this is combine. Okay, combine. So when combine, so the carrier follows the shape of the modulating signal. Okay, and then what? So you see that from here, what happened is that if you see from this graph, this is during the positive side, the positive side and the negative side. During the positive side, the LC tank circuit will charging. Okay, during this cycle, LC tank circuit will charging, and during this cycle, LC tank circuit will discharge. Okay, and for your information, when we move to point B, okay, point B, during the diode prevent the reverse bias, so current cannot flow from the other direction. Okay, so what happened is that you see that instead of having this negative cycle, it has been cut off. Okay, the negative cycle has been cut off actually. Okay, so actually there's another negative cycle over here, but it is actually been cut off by the diode. Remember, the function of diode is like a switch. Okay, where it only allows current to flow in one direction only and prevent reverse bias. So diode is like a switch. Okay, it's like a switch, on and off switch. Okay, and you see that the negative cycle the negative cycle of the signal has been cut off. Okay, so how to compensate this? Okay, so what happened is that at point C, okay, at point C, the LC tank circuit will compensate the cut off wave. Okay, so LC tank circuit, you see that during the forward bias, LC tank circuit will charging, and during the reverse bias, LC tank circuit will discharge to compensate the cut off wave. And then this is charging, forward bias, and then reverse bias, LC tank circuit will discharge. Forward bias charging, reverse bias discharge by the tank circuit, and then discharge again by the tank circuit, discharge by the tank circuit. So this happens very quickly. Okay, so the charging and discharging happens very quickly, so you can see that it compensates the cut off wave. Okay, so these are the answer for the previous semester questions. Okay, students are asked to draw the waveform at 3 different locations, A, B, and C. Okay, so you see that how does the tank circuit discharge? During it will discharge when it resonates at carrier frequency. Okay, you see that LC is resonate at carrier frequency, causing oscillation, creating negative half cycle for every positive cycle. Okay, so resonate means that it will resonate at the same frequency of the carrier frequency. Okay, LC resonate at the frequency of carrier. Dia akan berayun pada frekuensi carrier. Okay, which creates a negative half cycle for every positive cycle. Okay, so this will compensate the cut off waveform by the diode. Okay, and then what? Transistor modulator. So in your notes, you will learn only 2 types of low-level modulator. So there are actually many types of low-level modulator available in the real-world scenario. Okay, but in your syllabus, we only put 2 low-level modulator circuits type. Okay, so transistor, remember transistor. So what is the job of transistor? Remember, transistor is also like a diode, which only allows current to flow in one direction only. So that means transistor is also a switch, same like diode. And then what else? Transistor is also an amplifier. Okay, so there are 2 main tasks of the transistor, which is allows current to flow in one direction, which is as a switch, and also to become as a amplifier. So this is the transistor. Okay, so if you see from here, okay, this is the transistor, and this is a okay, so you see that the above part here is the collector to the emitter, okay, and if you remember that current flows from collector to the current flows from the collector to the emitter to the ground. Okay, so current can only flow from collector to the emitter if only the voltage at the base above the threshold limit. Okay, if only VB more than the more or equal than the more than the threshold limit VTH, okay, VTH, then the current can flow from collector to the emitter. If the voltage, if the base voltage lower than the threshold, then current cannot flow. It's like a reverse bias. Okay, seolah-olah seperti reverse bias. Okay, so at the base, the carrier and the information signal will mix together. Okay, and when the during the positive cycle, that means the amplitude is larger than the threshold, because threshold is around 0 point something, 0.7 or 0, depending on the type of transistor. Okay, so at that when during the positive cycle, the base voltage more than the threshold voltage, that means currents can flow from collector to the emitter. At this case, the tank circuit will charging. Okay, and when the base voltage drop below than the threshold voltage, current cannot flow from collector to the emitter. Okay, so in that case, it will cut off, the waveform will cut off, and at the same time, LC tank circuit resonate at the carrier frequency, and it will compensate the negative output. Okay, so you're gonna get a full AM envelope at the output. Okay, so the how does this works is similar with the diode modulator. Okay, similar with the diode modulator, only this time we use the transistor, which play around with the voltage at the base. If the base voltage above the threshold limit, current can flow, that means LC tank circuit will charging. And when the base voltage drop below the threshold limit, current cannot flow from collector to the emitter, and based on this, the LC tank circuit will discharge to compensate the negative cycle, okay, during the cut off by the transistor. Okay, high level AM. High level AM, also there are two types of high level AM. Okay, in your notes only two, which is what we call as a collector modulator and series modulator. In the real world scenario, there are more than two. Okay, there are more than two available in the real world scenario. So for collector modulator, okay, collector modulator, you see that here we use power amplifier, and also use the high power audio amplifier and transformer. Okay, so this is the collector and flows to the emitter, to the ground. Okay, so here is VMT is over here, and then amplify the input message. Okay, and then another amplify by the transformer. Okay, so it produces a higher voltage, and the current flows from VCC to the ground only if the voltage at the base more than the threshold limit. Okay, during the positive cycle, when base voltage more than threshold, the LC tank circuit will charging, and when the base transistor drops below the threshold limit, this LC tank circuit will discharge to compensate the negative cycle. Okay, so therefore you're gonna get at the output is a full cycle of AM waveform, a complete AM waveform. Okay, and this is a series modulator where we use two transistors connected in series. Okay, so each transistor is connected to the VMT, and another one connected to the carrier. Okay, so this is connected to the message, this one connected to the carrier. Okay, and current flows from the collector to the emitter. Okay, current flows to the connector and the emitter. And during when you see that when the voltage at the base more than the threshold limit, then similar with here, current can flow from carrier to the ground. Okay, if the voltage drop below the base of the below the threshold, that means the current cannot flow straight like this. Instead, it will move to the other side. So so what happened is that, sorry, So during the negative cycle, during the positive cycle, current can flow over here. So this LC tank circuit charging, but during the reverse bias, current cannot flow from collector to the emitter. Okay, so what happens is that this LC tank circuit will discharge. It will discharge to produce the output, to compensate the negative half cycle. Okay, so imagine that if only one of the amplifier is below the base threshold, current cannot flow from VCC to the ground. Instead, the LC tank circuit will resonate and produce the half cycle of the output. Okay. Circuitry of the double sideband suppressed carrier. So up to this slide, we are actually learning how to produce double sideband full carrier. Okay, how to produce double sideband full carrier. So we have two types of modulator: low level and high level. Okay, low level we have a diode and transistor. Here we have collector, modulator, and also series modulator. Okay, so all of these produce the double sideband full carrier. Okay, circuitry for the double sideband suppressed carrier. So circuitry for the double sideband suppressed carrier is using the balance modulator. So this is the balance modulator to produce double sideband suppressed carrier. Okay, so I want to explain about this. Okay, I want to explain about this. So you see that the carrier is over here at the ground, at the lower side here, carrier, and this is the modulating signal, the VMT. Okay, this is the VCT. Okay, so what happened is that okay, so from here you're gonna see that we have two transformer from the circuit, T1, T2. Okay, over here is actually also transformer T3 actually. So we want to see how does the circuit works. How does the circuit works? Okay, so you can have a basic understanding about this. Okay, you can have basic understanding about this. Okay, so I will show you how does the circuit works. Okay, so first of all, you need to know that there's a VMT on the left, VCT on the ground, on the lower side, and we have a transformer separate the modulating signal and also the output. Okay, so we have T1 and T2. So you see that this circuit operates by activating only two diodes in one at one time. At one time, only two diodes will operate. Okay, D1, D2, or D3 and D4. Okay, so this is what we call as a balance modulator or lattice modulator. Okay, so what happened? So now we're gonna see that during the positive cycle of the VMT. Okay, during the positive cycle, positive minus like this. So carrier has a higher frequency. That means carrier change frequency, carrier change polarity many times compared to the modulating signal, because carrier has higher frequency. So it is rapidly change polarity positive negative for the carrier. But for the VMT, it takes some time because the frequency is lower. Okay, so what happened? So during the positive and negative polarity of the carrier, so the current will flow in this direction. Okay, and then it will split over here. Okay, so you see that the splitting is depending on the tapping point over here. So that's why the tapping point over here need to be at the center, so that current can be divided into two upper and lower. So, and then you see that the current flows in these directions. Okay, so this diode D1 will be forward bias, similar with D2 will forward bias. Okay, will forward bias, so current can flow. But for D3 and D4 will cut off because of the reverse bias, so current cannot flow in this direction. Okay, so what happened is that, so current flows. Okay, current flows. So in this case, D1 on, D2 on, D3 off, D4 also off. Okay, so current flows in these directions. Okay, and produce the output. Okay, it produces the output. So how does the output looks like? Okay, so I take this from the Wayne Thomas's book. I take this from Wayne Thomas's book in order to further explain to you about the waveform. Okay, so that you can have better understanding. Remember previously I put a single this one, positive and negative. Okay, so you can see from this part, the first half. Okay, the first half. Okay, the first half. You see that this modulating signal only for a single cycle, and carrier already done for how many cycles? So for already 1, 2, 2.5 cycle. Okay, already changed 2.5 cycle. Okay, so what happened at the output? Okay, so when D1 and D2 switch on, okay, so you see that the carrier, so it will change this one. The output gonna be like this. It follows this one. So it follows the output half of this, and then this is D1 and D2 switch on. Also, I forgot to explain D3 and D4. Sorry, wait. So this is during D1 and D2 switch on. Okay. So what happened during D3 and D4 switch on? Okay, so this is when polarity of the carrier like this. So I erase I erase to show the other polarity. So saya padam sekejap. So I will erase this to show the changes of polarity. Okay, so now the carrier polarity change, positive, negative. What happened? Okay, so what happened is that the current will flows into this direction, and then it will split into two like this. Okay, so one will go through the D3, and the other will go through the D4. So D3 and D4 will switch on, forward bias, while D1 and D2 will cut off. Okay, so D3 will on, D4 will on, D1 off, D2 off. Okay, so current will flows into this direction. Okay, so what happened is that, so you're gonna see how the current flows in the other side. Okay, so what is the output? How does the waveform looks like at the output? Okay, so when you see that this is positive, this modulating signal still has the same polarity. Carrier signal already changed a few times. Okay, already changed polarity a few times. So this is from Wayne Thomas's book, chapter 6. Wayne Thomas's, you see that figure 6 means that chapter 6. So during this part, during the first half of the carrier, D1 and D2 will switch on. Okay, and then the carrier change polarity. D1 and D2 switch off, instead D3 and D4 will switch on for the other half. Okay, and then D1 and D2 switch on, and then switch off, and then D3 and D4 switch on, and then D1 and D2 switch on. So you see that the first half, the output follows the polarity of the carrier. Okay, it follows the polarity of the carrier for the first half. Sorry, for the first half of the modulating signal. And what happened here is a 180-degree phase shift, which is when the polarity of the modulating signal change, like this, polarity of the modulating signal change, negative and positive. So when the polarity of the modulating signal change, the output signal will inverse. Okay, the output signal will inverse. What happened? What happened? So you see that when the carrier signal move to the negative polarity, what happened is that the output will produce positive polarity. D1 and D2 will switch on. And then carrier, so now we are here, negative. Okay. So now, this one, so it positive cycle of carrier produce negative cycle of the output. Negative cycle of the carrier produce positive cycle of the output. Positive cycle carrier produce negative, negative carrier produce positive. So these changes at the output is controlled by the diode, D1, D2, D3 and D4. Okay, and of course the output signal is not smooth like this. In order to make it smooth like this, we need to use filtering circuit to produce a smooth output. Okay, so this is what I have shown you before, the graph number D. Graph D, this is what I have shown you before, how to draw a double sideband suppressed carrier, where I draw the imaginary line, this one, the imaginary line, and then I draw the waveform, and then I stop in the middle, and then the graph is inverse. Instead of going down, it inverse like this. Okay, so what you need to know is how to draw, okay, as I have told you before, like this. Okay, so you need to draw like this, and then reverse this. Okay, so I repeat again. Okay, I repeat again. So see what I have drawn. This is a V versus time. Okay, I draw the imaginary line, and then I start drawing. Okay, I stop. So instead of I'm continue downwards, I need to inverse the signal to become upwards like this, because this is 180-degree phase shift. Okay, 180-degree phase shift. Okay, sorry, so I repeat again. So here you see that here becomes like this. Okay, so this is what we call as the, maybe I use different color. This is what we call as the 180-degree phase shift. Okay, so you have seen what happened in this picture. So D1 and D2 control the control the polarity at the output. Okay, control the polarity at the output, and when the VMT change polarity from positive to negative, the output signal will inverse from the previous. Okay, so the polarity at the beginning follows the polarity of the carrier, and then when the VMT change polarity, the output will have a different polarity compared to the carrier. Okay, so up to now we haven't asked you to draw this picture. We haven't asked you to draw this picture yet. Okay, belum pernah ditanya berkenaan dengan gambar rajah ini. We haven't asked student to explain about this. Okay, but we have asked the student to draw the frequency spectrum. Okay, frequency spectrum we have asked a few times about the double sideband suppressed carrier. So for the frequency spectrum, okay, which is V versus F, okay, what you can do is that this is FC minus FM, this is FC, this is FC plus FM. Okay, so there are only two sideband, which is this is VLSB and VL. This is VLSB, this is a VUSB. Okay, and there's no carrier component. So in terms of power total is equal to PLSB plus PUSB only. Okay, there's no carrier component. Okay, so remember the VLSB and VUSB is not equal to VM over 2. Okay, remember this is not equal to VM over 2. How much is it? The value depending on the equation. So that's why it is very important to define the equation first. Then you can find the total power. Okay. So so this is the total power for double sideband suppressed carrier. Remember, we only have two components. You see that here we have two components only, no carrier component. Okay. Single sideband circuit. So there are two methods of generating the single sideband signal. First, using the filtering method. Second, using the phasing method. Okay, so to generate the single sideband using the filtering method, what we do is we can use the so here you see that filtering method, we use this filter. So at the beginning we have the balanced modulator, which produce double sideband suppressed carrier. Okay, so this is the carrier VCT. This is the VMT. Okay, so these produce the double sideband suppressed carrier, and then we have the filter over here to choose either upper or lower. So this carrier, so this will in this example, this filter choose the upper sideband and remove the lower sideband. In this example, actually you can also choose the lower sideband, no problem. Okay. So the output here is single sideband, and then amplify, and then we can transmit the signal. Okay. Another filtering method is this one. Okay, is to use two filter, upper sideband filter and lower sideband filter, which has a switch over here. So we can control either to choose the upper sideband filter to choose the upper sideband, or to choose the lower sideband. Balanced modulator produce double sideband suppressed carrier. So when we produce double sideband suppressed carrier, then we can choose either to choose the upper or lower sideband. Okay, and then frequency translator, and then we amplify the signal and then send the signal. Over here, picture B, we use single filter but two carrier frequency. Okay, 2 carrier frequencies goes through the balance modulator. Again, we will produce a different set of double sideband suppressed carrier, and filter is to choose upper or lower sideband frequency. Okay, and then frequency translator and then transmit. And then the second method to produce a single sideband suppressed carrier is by using the SSB generation phasing method. This has been come out in the previous test and final exam a few times. Telah ditanya beberapa kali. Okay. So for example here, balance modulator. Okay. So this is we have 2 balance modulator, 1 and 2. So you can take note about my explanation because there's no explanation over here, so maybe I can do explanation here. So we have here VMT. VMT, for example, we use a VM sine 2 pi FMT. Over here we also have carrier. Carrier is equal to VCT. Also we use sine, VC sine 2 pi FCT. Okay. So you see that modulating signal goes through the first balance modulator, and then this modulating signal goes through the 90-degree phase shift and then go to the second balance modulator. So what happened in the 90-degree phase shift? 90-degree phase shift for a sine wave will produce cosine. So over here it becomes Vm cos 2 pi FMT. Similar with carrier. Okay, it becomes Vc cos 2 pi FCT. Okay, so you see that here in the first balance modulator, sine wave multiplied with sine wave. So balance modulator, what happened is that it will multiply the signal. Okay, so what happened at the output here, output A, for example A, so this becomes Vm multiplied with VCT. Okay, so what happened is that you're going to produce Vm VC sine 2 pi FCT sine 2 pi FMT. Okay, and according to trigonometry identity, you can rearrange the equation. Okay, this one use trigonometry identity becomes Vm Vc over 2 in bracket cos 2 pi, this one is lower sideband Fc minus Fm T minus cos 2 pi Fc plus Fm T. So this is what we have learned previously. Okay, cos minus cos, lower sideband and upper sideband. Okay, and then what? And then you see that at the second balance modulator at point B, so what happened here is also VMT multiplied with VCT. Okay, so you're going to produce this one similar with the above, Vm Vc, but now it is in terms of cos 2 pi FCT cos 2 pi FMT. Okay, so according to trigonometry identity, we can do like this, Vm Vc over 2. Cos and cos, you're going to produce cos plus cos. Okay, cos plus cos. So cos 2 pi Fc minus Fm T plus cos 2 pi of the upper sideband, Fc plus Fm T. Okay, plus Fmt. Okay, close bracket. So you see that we produce A and B, the output of balanced modulator. Balanced modulator, remember, it will produce the multiplication process. So balanced modulator, if you see the symbol is X. You see that symbol X. X here means that multiplication in the equation, in the math equation. Okay, and then at point C, you see that this is adder. So you need to add above and below. So when you add above and below, you see that what happened? Okay, you see that when we add above and below, so this upper sideband can be cancelled out because this is minus and plus. So we can cancel this. Okay, so the lower sideband, so it becomes at C, at point C, this is Vm Vc. Okay, Vm Vc. It becomes Vm Vc because this is a Vm Vc. Sorry, Vm Vc cos 2 pi Fc minus Fm. The lower sideband. Okay, Vm Vc over 2 plus Vm Vc over 2, so we get Vm Vc cos 2 pi Fc minus Fmt, the lower sideband. Okay, so this is at point C. What happened at point D? For example, here A is equal to 10, for example, the gain. So at point D, it is equal to 10 Vm Vc cos 2 pi Fc minus Fm T. Okay. And if you draw the spectrum, it becomes like this. Okay. So there's no carrier. Okay. There's no upper sideband. And there's only lower sideband, which has the amplitude of 10. Okay, and if you want to calculate the power, because we have asked this previously, calculate until the power, calculate the total power. So the total power in this example is equal to PLSB. Okay, which is equal to 10 Vm Vc square divide with 2R. Okay, V peak square divide with 2R. So we get the value, so we get the value in terms of what? X what? Finish. Okay. This has been asked in the previous example, in the previous test or exam question a few times. Pernah ditanya beberapa kali. What about if you are asked about the bandwidth? How much is the bandwidth actually? So the bandwidth, if you see from this, the bandwidth is Fm. Okay, the bandwidth is equal to Fm Hertz. So I already gave you the previous semester's question answer. Any question you want to ask about this? Student, are you still there?
Yes, Doctor.
Okay, thank you for the response. You want to ask any question about this? Do you understand? Just remember that balanced modulator do the process of multiplication. you multiplied VMT and VCT in this example. So balanced modulator multiplied both input. Mathematically, it will multiplied. Okay. Any question? Semua dah nak balik Okay. Okay, question 1, 2, 3. Okay. Betul tak ada soalan Okay, so if you don't have any question, I will stop here exactly almost 5 p.m. Almost 5 p.m. Okay, I already explained this, and we can take the attendance. So if you want to see what is the kind of question that have been asked previously, please look into the question banks, test and also final exam. We have asked this kind of question a few times. Okay, so you can open your QR code reader, and you can take the attendance, and then you can go out. Regarding the quiz, okay, regarding the quiz, please see my message from in the WhatsApp group, so that you can confirm the date. So currently we agree on Saturday. Okay. Unless if anybody is not available at that time, we can change to other date. Okay, so for now it's on Saturday. Okay, so if nobody object the proposed date, we will proceed. Okay, so that's all for today. See you again next week.
Thank you, Doctor.
Okay, welcome.
Thank you, Doctor.
Welcome.
Thank you, Doctor.
Okay, welcome. Welcome.
Thank you, Doctor.
Welcome.
Thank you, Doctor.
Okay, welcome.
Terima kasih, Doktor.
Welcome.
Thank you, Doctor.
Okay, welcome.
Thank you, Doctor.
Welcome.
Doctor.
What's your name?
Gu Beijing.
Pardon?
Gu Beijing.
Which one?
GOO.
Oh, Gu Pei-Ching. Okay.
Yes. Thank you, Doctor.
Okay, welcome. Who else?
Doktor, saya pun tak dapat scan.
Okay, nama siapa?
Nazirul Faris, nombor 16.
Okay, Nazirul Faris. Okay, done.
Yeah,
Same here, Doctor. Number
Doctor.
6.
Number 6, what's your name?
Alasadi Hazim.
Alasadi. Okay.
Thank you.
Welcome.
Doktor, nombor 19, Mugilesh Saminathan.
Okay, done.
Thank you, Doctor.
Welcome. Who else? Anybody? So, if nobody, 3 students absent. Lagi ke? Ahmed Samir already take the attendance or not? Ahmed Samir, wait. Ahmad Samir already take the attendance. Okay. Okay, so that's all for today. Stop presenting.